Hello everyone, I'm Dr. Matlab. We resume our course. We have got this inequality and we said we will propose some numerical examples in order to show you how to apply this inequality in order to determine how many digits after decimal point we can keep while keeping the good precision. Okay? We can start with this numerical example that we have proposed in the previous video. Now we will show you how to apply this inequality in order to determine how many digits after decimal point we can keep for this pole. Okay? In fact, we will propose two methods. The first method I will propose, it's more practical. The second method, it's more complicated, but it can be more accurate, more precise, and can allow you to understand better this inequality. Okay? Anyway, it's up to you to choose between these two methods. I will start with the first method. We will apply this inequality, we replace z by the value of our pole, and we obtain this inequality. Delta z have to be less than this value. Now we have our pole. What does the first method propose? We account the number of zeros between decimal point and the first digit, which is not equal to 0. We can find that we have 3 zeros. Now we add 1 to this number, so 3 plus 1 is equal to 4. So we will keep 4 digits after decimal point. Okay, so our pole after the modification is equal to 0.99. Okay, so this is the first method. We account the number of zeros between decimal point and the first digit, which is not equal to 0. Then we add 1 to this number. Then we obtain the number of digits to keep after decimal point. For the second method, in place of delta z, we put here z1 minus z1 prime, and after mathematical development, we can get this inequality. Now we have our pole. Okay, now how to do in the second method? We try to keep 1 digit after decimal point, then we check this inequality. That means we ask the question, is z1 prime higher than this value? We can observe that z1 prime is not higher than this value, so this inequality is not verified. Okay, now we try to keep 2 digits after decimal point, and we check the same inequality, and we ask the same question, is z1 prime higher than this value? We can observe yes, so this inequality is verified, so it's okay to keep just 2 digits after decimal point. If this is the second method, we start to keep 1 digit after decimal point, then we check this inequality. If it's okay, so we keep just 1 digit after decimal point. If not, we try to keep 2 digits after decimal point, then we check the same inequality. If it's okay, so we keep 2 digits after decimal point. If not, we try to keep 3 digits after decimal point, and so on. Okay, so we continue until this inequality is verified. Now we obtain this transfer function where the pole is modified. That means we kept just 2 digits after decimal point. Now what can you observe? In fact, the gain before the modification, it was equal to 1, but after modification the gain was changed. Now the gain after the modification, it's equal to this value, which is not equal to the gain before the modification. In fact, we have to keep the same gain before the modification. We don't have to change our gain. Okay, it's true we modified our pole, but we don't have to change our gain. So how to do? Quite simply, we can multiply this transfer function by this ratio, which is equal to the gain before the modification over the gain after the modification. Okay, so now we multiply this transfer function by this ratio and we obtain our final transfer function. As you see here, we kept the same gain before the modification. We can replace z by 1 and we calculate the gain after the modification. We can find it's equal to 1, which is equal to the gain before the modification. Okay, we can propose another numerical example. We can start with this 0. We can find 2 zeros between the decimal point and the first digit, which is not equal to 0. So we have two zeros. So 2 plus 1 is equal to 3. So we have to keep 3 digits after decimal point. Okay. Now for this pole, we can observe that we have a negative real number. It's not a problem. Natural logarithm can give a complex number. Finally, we will calculate the norm, where the norm is a real positive number. Okay, after calculation, we can find that we have 1 0. So 1 plus 1 is equal to 2. So we will keep 2 digits after decimal point. Now we consider this pole, and we can observe that we have 4 zeros. So 4 plus 1 is equal to 5. So we will keep 5 digits after decimal point. So here is the transfer function after the modification. Okay. Now we will adapt our gain. We calculate the gain before the modification and the gain after the modification. Here is our final transfer function. We modify the zeros and the poles, and at the same time we kept the same gain before the modification. We propose another numerical example where we have two complex conjugate poles. We can start with this 0. We can observe that we will keep 3 digits after decimal point. Now we consider this complex number. Just we note that for a complex number, we consider here 0.005 instead of 0.05. It's just to be more precise, more accurate. Okay. So if we have here a complex number, we consider here 0.005. We calculate, we can find we have two zeros. So 2 plus 1 is equal to 3. So we keep 3 digits after decimal point for the real part, and 3 digits after decimal point for the imaginary part. Okay. Now we do the same thing for the complex conjugate number, and we obtain this transfer function after modification. Now we correct our gain. So we calculate the gain before the modification and the gain after the modification. So we can find our final transfer function after the modification. Okay. Now for numerical application, we don't have to leave this transfer function with complex numbers. So we multiply these two polynomials of degree 1, and we obtain here a polynomial of second degree. Okay. Here is the general factors form, and we modify the zeros and the poles just for this part, n of z over d of z. Okay. Now we can take this example where we have already proposed this numerical example, and we obtain this transfer function after the modification. Finally, we have this transfer function to be considered to be applied. Okay, I stop here for this video, and we will continue with our procedure in the next videos. So wait for me, and please don't forget to subscribe to my channel. Thank you for your watching. Goodbye.